In this video, we will use derivatives as approximating functions. We have seen this before, so it's just more examples. And basically, we will use the tangent line as an approximation of the function at that point. So we have seen already, let me put the video on top. Okay, so we have seen already that if you have a function and you, at this point, sum x equals a, and you want to approximate the function at x, you could use the tangent line as the approximation of the function at this point. So f of x, or this y here, this y, would be, so this is f of x, it's this height, which is f of a, right? F of a is this height, plus this height, right? And that height comes from the slope times this distance. So it's f prime of a plus x minus a. In fact, this is the equation of the tangent line, right? Y, this height, as a function of x. But it's given as this height fa plus the derivative of f at a times the change in x. We could also basically say that we have dy over dx as f prime at a. So dy, this height, the additional height, dy, is shown as, it's called the differential times dx, where we call this distance dx. So y minus fa, y is this whole height minus fa. So y minus fa is equal to f prime a times x minus a. Okay, so y minus fa can be called dy, the differential, this vertical height, which is equal to the derivative f prime a times dx, and dx is how much displacement we have done in the x direction. Okay, so we have this approximation of the function about the point A, okay? And we can also write it as that we have a differential dy. That means from fa, how much more we add is given by f prime a times dx, where dx is given as this. Okay, so dy over dx is not dividing dy by dx when you write dy by dx, because that is just the notation for derivative, right? Leibniz notation. However, when we write dy, then we mean this differential. Okay, that is the differential. So we have the linear approximation of the function given here, and we have the differential given here. So that's basically the entire chapter. We will just do examples of both of these, not chapter, but this section. Okay, so the linear approximation y is given by this formula. All right, so for example, square root x, and we want to approximate at x9, but use that approximation at x equals 9. So this a is 9 to obtain this. So we use the linear approximation formula. Lx, the function is f at 9, f plus f prime at 9, plus x minus 9. Okay, what is x? 9.1. So dx is basically 0.1, right? So plug in the values, plug in 9.1 for this. Okay, so approximation of the linear approximation of the function at 9.1, or square root of 9.1, will be 3. F of 9 is 3, plus its derivative, 1 over 2 square root x, right? Plus times 0.1. And so this is f of 9. This is f prime of 9, 1 over 2 square root x. And you just plug it in, and you get the approximation of the function. Okay. Similarly, find the linear approximation of sine x at x equals pi over 3 and use it to find sine 62 degrees. So 62 degrees is 60 degrees, which is pi over 3 radians, plus 2 degrees, how many radians that is. So radians means it'll be 2 times pi over 180, right? So pi over 90 degrees will be this 2 degrees extra. So we apply this, where we take x, which is pi over 3 plus, so this difference is just 2 degrees, which is pi over 90 degrees, radians. And sine of pi over 3 is here, plus derivative of sine is cosine, cosine of pi over 3, times pi over 90 degrees. So that's in radians. And that will be the approximation of sine 62 degrees. So sine of pi over 3 is square root 3 over 2. Cosine of that is 1 over 2. Plug in sine and cosine. And then x minus pi over 3. So 62 degrees is 180. Right? So 62 pi over 180 degrees, but we have to subtract pi over 3 from that, right? So, or do just 2 degrees. Okay, plug that in and you find the approximation. So this is the sine function, but we are approximating the function by this straight line, just near it, near a point, right? So if you go far, then the approximation won't be as good. Okay, so for example, this one, at x equal to 0, to estimate 1.013. So once again, our this is just a, this is a, and 1.01 is x. Oh, not x, will be 0.01 here. 0.01 will be x. Okay, so our linear approximation is this. Our function f0 is 1. F prime 0 is n. Take the derivative of this, which is n times 1 plus x to the power n minus 1. Plug in x equal to 0, so it becomes n. So here we get our function. Okay. So now we need to evaluate, so it becomes basically 1 plus nx is the approximation of the function. And plug in 1.01 for x. So f of 1.01. So plug in that for x. So 1 plus n. N is 3 here. And L of 1.01. So here we get 1 plus 3.01. Okay, so this x minus 0, so there is a typo in the problem. Okay, so it's 1 plus x to the n so x minus a so x minus a is 0.01 and not 1.01, as you can see, right? So this is not L of 1.01, it will be L of, or F of 0.01, or L of 0.01, okay, from that point. And this should be x minus, or if you want to write x is 1.01, this should be kept as x minus 1. So this is the typo. It should be 1 plus n, x minus 1 is the correct answer for Lx. So there's a typo here. So now you can say L of 1.01, you plug in 1.01 here, and we get 1 plus n times 0.01, and n is 3 here. Okay, so please be careful about this typo. in the book. The only mistake is this should be 1, and that of course changes the formula. Then this is correct, and this is correct. Okay, then differentials we already studied, or I explained what a differential is. So for example here, y, find dy. That's pretty straightforward. Just do the derivative dy over dx, which will be 2x plus 2, and then the differential dy is equal to 2x plus 2 times dx. If x is 3, plug that in here, and dx is 0.1, plug that here. So here is the formula for that. So 2 times 3 is 6, plus 2, 8 times 0.1, so 0.8. Similarly for this one, dy is the derivative, which is negative sine x times dx. Okay, pretty straightforward stuff. And as I said, here's the function. Here is the point a, and we are taking this to be dx. We're going to a plus dx, and this height is dy, f prime a times dx. Okay, so y is x squared plus 2x. Compute delta y and dy. What is the difference between delta y and dy? Now delta y is actually, if you take the value of the function here, f of a plus dx. So delta y is f of a plus dx minus f of a. So it's this height, the whole height here. And what is dy? Dy is just the linear approximation height, dy. So in general, if you don't go too far, if dx is small, a function is differentiable, then they should be close to each other. So we can approximate delta y by dy. But normally, if you go farther away, then it can be different. So here we have the function, and dy is simple, right? Dy is just derivative of this, which is 2x plus 2 times dx. X is 3, so this is 0.8 times dx. But what is delta y? Delta y is the function, so let's call it, this is the function, at a plus delta x, so 3 plus, so f at 3.1 minus f at 3. That will be delta y. Okay, f of 3.1 minus f of 3. And that turns out to be 0.81. And dy, which is f prime 3 at 3.8 here, so it's very close to that. Okay, we can also find the amount of error. For example, if you're finding a volume of a cube, right, and you have some measurement error in, so the volume is given by x cubed. And now, if you have a measurement error in measuring x, how much of the error will go to the value of v? So this is also obtained by basically looking, so we can approximate that by saying dv. What is the dv? So this will be 3x squared dx. So let's say, so x is 5 centimeters, but with an accuracy of 0.1 centimeter. So dx is between negative 0.1 and positive 0.1. Use differentials to estimate the error in the computed volume. So dv will be between 3x squared times dx, positive and negative. That will be the error in the volume. Okay? And you will see that that is also close. If the measurement error is small in x and the function is, smooth function, differentiable function, then the error in the function will also be small. So we can approximate it by using the differential. Okay, so I will, now percentage error or relative error. Relative error in something is, once again, let's say radius of Earth. Radius of Earth is given by 4,000 miles with an error. So this is R, this is dr, to percentage error now instead of error. So we found the error in volume before. So the volume of the Earth. Volume of the Earth is 4 by 3 pi r cubed. So dv is 4 pi r square, right? dr. If dr is between this and this, our error dv will be between 4 pi r square times 80 and 4 pi r square negative 80 when r is 4000, right? So dv is this. Then to get the relative error, you divide by v. But the thing is, our v is not accurate, but because our nominal value is 4000 with an error of plus minus 80. So for relative error, we can use the 4 by 3 pi r cube, where r you take 4000 and divide by that. So I mean, the best guess, right? I mean, plus minus error is there. So divide by this value of volume and say that the relative error is this, between this and this. And if you multiply by 100, it gives you in terms of percentage. So it's plus minus 6%. Okay, and this finishes this section of the